today I'm going to be talking about epidemiology, just some of the basics, and I feel it's always good to get a little bit of a sense of where people are before I go into this talk. So if each of you could share with me a bit about maybe your exposure to doing any kind of cohort studies or calculating odds ratios.
My name is Nadia. I'm in Dr. Nelson's lab doing research for her this summer. I'm a rising second year medical student, and I majored in public health, so I took biostats courses.
Okay, so you have a lot of exposure then.
A moderate amount.
Okay, all right, great.
And I also have my master's in public health, my PhD's in public health. So I have like 101 courses that I've taken for epi, and then I calculate odds ratios if I have dichotomous outcomes, but I haven't actually worked on any epi data for writing a paper or anything.
Okay. Okay. Oh yeah. How about Emma? Is she able to?
I think she is muted. She's muted. Oh.
Were you asking about my background in epidemiology?
Yes.
So I majored in public health in nutrition. So I took the Epi 101, but that's about it for my background.
Okay.
I'm working with a lot of epidemiological data this summer though, so
Right.
sure whatever you're about to say will be very helpful.
Yeah. So some of this today will probably be a little bit of a review for some of you, but some of it, the way I've structured this, I've tried to make it apply to what your projects might be over the summer, some of the methods you'll have to use. Okay, so thank you, Emma. What is epidemiology? What we're doing is we're looking at the health of a population. So the population can be defined as a certain group of individuals we're looking at. It can be just a community. It can be a clinical sample that we're interested in. So the main point of what we're trying to do in epidemiology is figure out how frequent a disease occurs. And then we're also interested in looking at the factors that are associated with that disease occurring. And so what we're trying to do in studying a population is we're looking at a cohort, which is just a group of individuals, and then we're trying to determine the experience of that population within a certain amount of time. So I have these figures here to try to walk us through what we're looking at. So a cohort is often, we need to define it for when we're doing our research. But a cohort is a group of people. That population may be changing with time, with some people entering the cohort, some people leaving the cohort. That's why it's kind of drawn here in this cloud, indicating that it's not always well defined until we as researchers come in and define what cohort means. And then we're tracking this cohort over time. We can look at it at just one point in time, or we may want to look at it at multiple points in time. And then we're interested in looking at all the exposures that act upon that cohort, and then seeing what health-related events or outcomes occur to this cohort based on whether they've been exposed or not exposed. So with this, anytime that we're doing our research, first of all, we need to have a well-defined research question where we have established up front, what is this group? How are we defining them? And what point in time or period of time are we looking at? So when we're looking at time, as I mentioned, we can look at just one point in time. So we consider this to be a cross-sectional analysis. And then we can also track over time, call this longitudinal analysis. And we're often interested in looking at individuals who don't have disease at baseline, and then seeing who develops disease over time. So I think you'll be working with Johnston County. So that's a common cohort that we work with here at the Thurston Arthritis Research Center. So some of the examples I'll be giving today are based on some of the work that I've done. But where Johnston County is located is just southeast of Raleigh. It's a predominantly rural county, and this is a study that began 28 years ago, where we've continued to follow more than 4,000 participants. So this is a timeline of the Johnston County Osteoarthritis Project. So we began enrolling our first participants from 1991 to 1997. And then we've had several follow-up time periods, as you can see here. But we also ended up bringing in more participants at this period that we call Team 1 Star, which was in 2003 to 2004. So when we do some of our analyses in Johnston County, sometimes we just pick one period of time. So maybe we're interested in everybody who was in the study in this period from T1 to T1 Star, and we have a number of papers just looking at one time point. And then we also have analyses where we look from the very beginning of the study all the way to our most recent follow-up time points. So there are many different kinds of analyses that can be done. When it comes to cohorts, we can talk about them as being either closed or open. So closed is where we have a very fixed time scale. So no one can enter or leave the study during follow-up except for death. This does not really fit the real world. It can be done if you're, have a study where you have a shorter follow-up time period, but we find, in the types of studies that we're doing in Johnston County, larger cohort studies, that they do have to be more open or dynamic, where we do have participants coming in at different times. As you saw, we had 2 different enrollment time points. Not everybody is followed up for the same length of time, because some of them are entering at different times. Some of them may be lost to follow up at different times. And that's okay. We have ways of trying to manage that in some of our analyses. So just to give an example here, so this diagram is just showing individuals where we're following them to see who goes on to get knee osteoarthritis. And so you'll notice we have 5 different participants. And if you're looking at when we began this study, in year 0, you see that we had 2 participants that started right at the beginning of our study, but we had others that entered into the study a little bit later. And so this would be a study that we consider to be open, and we would say open on the left. And so what we do is we follow each participant, recording when they either went on to get osteoarthritis, when they may have died, or when they were lost to follow-up. And for this, by the end of the study, 1 individual never developed osteoarthritis. So that gives you an idea of what the open cohort looks like. Going the wrong way. Okay, sorry. So for measuring disease occurrence, there are a few different ways that we can do it. We can look at prevalence. So this is looking at the frequency of disease at just one time point. So this would be the cross-sectional analysis. And the way that we calculate this is we just count up everybody who has the disease that we're interested in, whether they've had it for a long time, we would consider them existing cases, or whether they're new cases where they've just been diagnosed. And then we just look at these individuals with disease compared to the total population at a given time point. So the numerator doesn't make any distinction between new and existing cases. So this is an example here using that same diagram that we looked at before. So maybe we're interested in the prevalence at just year 4. So here, where'd my arrow go there? Okay. So here we see that there's 1 individual who has osteoarthritis when we look at year 4. This individual didn't end up developing it till later. So if we were to do our calculation of prevalence, we would say that at that time point at year 4, there was just 1 case out of a total of 5 subjects. So the prevalence would be 20%. But you can see how, when you select the time where you do this analysis, you may get different results. So if we look by year 5, now we have 2 people. So we would say that this was a prevalence of 40%. Incidence is sometimes called incidence proportion or risk. And so this is calculated in a similar way to how we calculate prevalence, but the difference is we're looking at new cases of disease. So we're not counting the people that already have existing disease. And the other thing that's important here is you have to state over what period of time you're looking at. So I'll give an example here. So this is an example where we're looking at ACL injury. So in this example, we have the luxury of having a closed study or a closed cohort. So on the left, everybody started at the same time period, and then we're following them for 10 years. So if we were interested in the 5-year risk of ACL injury, what we would see here is that we have 2 individuals who have ACL injury. So we would count the new cases that occurred and then divide them by the total sample. And we would say that the incidence or the risk is 40% over 5 years. So always saying that time period. And then you could also look at the 10-year risk for ACL injury. And this is one where we'd have 3 people out of 5, so 60% over time, over 10 years. So again, the important thing here is you're counting new cases and you're defining that risk period in terms of time. And then another example here that I'm giving, this one's a little more not as straightforward as prevalence and incidence, but I think it's important to discuss. I don't know if sometimes when we do our analyses, we do calculate rates. I have seen people sometimes misuse the term rate when they actually mean risk. So I feel it's important to at least go over this definition. So what you're trying to do here is you're looking at the person time, so the time at risk that each individual contributes to the analysis. So similar to calculating incidence, you are still looking at new cases that develop over a given period of time. But now for each individual, you're accounting for the fact that they may have contributed a different amount of time to the study, or a time that they were at risk in that study. So here's an example. It's actually very similar to what we were looking at previously with osteoarthritis. And what we're doing here for the denominator is we're actually calculating how many years that person was in the study at risk. So the first one, this person was in the study, did not develop OA, and then died at year 5, so they contributed 5 years. And then the next one, we're looking at osteoarthritis that was developed at 4 years. So once that person develops OA, they're no longer at risk. So we stop at 4 years for counting their time at risk. And then we have an individual here that we lost to follow-up at 6 years, but they hadn't developed OA during that time, so we count the whole 6 years. And then the next person contributed 4 years before they developed OA. And then this person was in the study for 8 years and never developed osteoarthritis. So our denominator ends up being the sum of all those years that they contributed at risk. And so we end up with calculating 2 cases per 27 person years. So this is something like on its own, it might not be very meaningful, but I'll give an example where we end up calculating ratios. So where you're comparing individuals who are exposed to not exposed, and that ends up being helpful in figuring out the rate that people are developing osteoarthritis. In looking at rate, we're looking at how fast they're developing it. It's kind of like looking at the speed of developing disease in a group that's exposed versus not exposed. And then for measures of effect, so this is the part that I'm going to be going into next, calculating ratios. But as I mentioned, we're trying to calculate the relationship between the disease and exposure. And so we're comparing how many people in one group who are exposed, develop disease, or have prevalent disease compared to those that don't have that given exposure. So there are a couple different ways that we can do those comparisons. I think probably more often we see in the literature calculation of ratios, so like odds ratios, risk ratios. And just for interpretation, we often consider, we consider a null finding to be a ratio of 1. Anything where it's more than 1, that's a positive association, so we're more likely to see a disease in a group that's exposed than non-exposed. If it's less than 1, we consider that a negative association. And then another thing that can be calculated are absolute differences. And then for that, a null would be 0. But the examples I'm going to be giving are with ratios, because I think that's more of what you'll be seeing this summer. So for the cross-sectional study, I mentioned that we calculate prevalence. And so the calculation for the prevalence ratio is quite straightforward. It's just looking at the prevalence of disease among the exposed compared to those who were not exposed. So the way that we calculate it here, so this is where we're looking at the association of knee injury and knee osteoarthritis. So we have a table here where we're stratifying and showing what the numbers are for knee injury and knee osteoarthritis as being 30. And then we want to see out of the total number of people who have knee injury, which is 40, how many of them have OA. So we would do 30 divided by 40. And then we would look at the non-injured group, so the non-exposed group, and we would have 35 who developed OA out of a total of 60 people who didn't have an injury. Sorry, yeah, that's right. And so what we would calculate here is we would do the prevalence in the exposed versus the prevalence in the non-exposed, and then we would have a prevalence ratio of 1.29. And I will share a copy of all these slides with you so you can see some of how we write about this. This gives some examples, like if you were writing your paper, an abstract of how you might interpret that ratio. So we would say the prevalence of knee osteoarthritis among participants with knee injury is 1.3 times the prevalence among those without knee injury. And then the odds ratio is calculated in a similar way to how we calculate the prevalence ratio. And actually the odds ratio is driven by prevalence. So odds is calculated as the prevalence divided by 1 minus the prevalence. So here we have the same table again. And the way that we would calculate it is we look at the odds of the exposed, odds of disease among the exposed, which is 30. And this time we divide it by 10, which is for those individuals who have a knee injury but don't develop knee osteoarthritis. So this gives us the odds for our numerator. And then for our denominator, we would have 35 divided by 25. And so ultimately the answer that we get here is that the odds ratio would be 2.14. And then similar to what you saw in the previous slide of how we interpret that, we would say the odds of knee OA among participants with knee injury is 2.1 times the odds among those without knee injury. And one thing I want to point out here, so you may have noticed that we got different numbers. So the prevalence ratio is 1.29. Yeah, that shows a positive association, but it's not a very strong prevalence ratio. But then when you're looking at the same table, when we look at the odds ratio, we have a much higher number. And one of the things that we have to consider when we're choosing between calculating prevalence ratio versus odds ratio is how prevalent the disease itself is. So here in this example, knee osteoarthritis is highly prevalent. So 65 people out of a total of 100 in this example have knee osteoarthritis. The prevalence ratio and the odds ratio are close if the disease is rare. So we tend to say a rare outcome would be less than 10%. But we do see that if you have an outcome that's more common, that the odds ratio overestimates the association. So this is just something to be aware of. You know, even as you're reviewing papers, if you see some really high odds ratios, but you notice that many people had the disease, that's just something to take into consideration as you review the literature. And then the next one is relative risk, or the risk ratio. So this is also calculated in the same way as how we would calculate the prevalence ratio, except this time we're having to make it clear that we're looking at a certain time period. So in this example, it's a 10-year risk of knee osteoarthritis. And then as before, what we do is we take 60, divide it by the total number of people, in this example, who have leg length inequality. And then we divide that by those who have knee osteoarthritis in the no leg length inequality group over the total number of 900. And in this example, we would say the 10-year risk of knee osteoarthritis among participants with leg length inequality is 1.2 times that among those without LLI. I know, not the most exciting thing, but hopefully this will be helpful with interpreting you know, your own results or reading other papers. So as I showed you earlier with looking at rates, this is where it becomes easier to interpret what we see with rates when we do it as a ratio. So I'll give this example here. As you might remember before, when we went through this table, or this figure, we had 2 cases out of 27 person years. And so for this example, I'm saying that this group now were the individuals who developed knee osteoarthritis in the leg length inequality group. And now I have done it for individuals who did not have a leg length inequality. And so we look at how many person years each contributed, and we add that for the denominator, and we end up with 2 cases for 36 person years. So here's where it becomes helpful, where we're interested in looking at those in the exposed group, what their incident rate is, compared to those in the non-exposed group. So those with leg length inequality versus those who didn't have a leg length inequality. And now we get a ratio of the 2 rates. And this lets us know that the rate is much higher or faster in the group that's exposed compared to the unexposed. And so we would say the rate of knee osteoarthritis among participants with leg length inequality is 1.33 times higher than the rate among those without leg length inequality. Any questions so far, or some of it familiar? So now I'll go into talking about confounding. So confounding is a source of bias that is often referred to as a mixing of effects when we're trying to look at an exposure and an outcome. And it turns out that there's some third factor that might be playing a role in any association that we see with the exposure and the outcome. So we consider a variable to be a confounder if it is a risk factor for the disease, if it's associated with the main exposure that we're interested in, and if it's not an intermediate step on the causal pathway. So I'll go through some examples to explain what all of that means. So here we're looking at the association between leg length inequality as the exposure and osteoarthritis as the outcome. And let's say that we're interested in seeing whether injury is a potential confounder in that association. So looking at risk factor for disease, what we see is that injury is a known risk factor for osteoarthritis. So that's where we would end up having this arrow here going from injury to osteoarthritis. And then we're interested in seeing whether injury is associated with our main exposure. So injury does lead, can lead to leg length inequality, especially children and adolescents while they're still growing, if they have a significant injury that can, to a lower limb, that can change their growth in that leg, and so they could develop a leg length inequality. And then the other thing that we look at is whether injury is on this causal pathway going from leg length inequality to osteoarthritis. So do we think that a leg length inequality leads to injury? It might in very rare cases, but generally we tend to think the arrow goes from injury to leg length inequality more so than somebody having an inequality and then going on to have a more serious injury. So we wouldn't consider, for it to be on the causal pathway, it would be an arrow going from here to injury and then injury to OA, and it doesn't seem as though it's on that pathway. So we would consider it to be a confounder because it is a risk factor for disease. It is associated with the main exposure, but it's not on that intermediate step it's not the intermediate step on the causal pathway. So what do we do if we end up learning that we have a confounder? Well, there are a few different approaches. So we can restrict our sample that we do our analyses on. So if, knowing that we think that injury is causing this mixing of effects, what we can do is just look at individuals who don't have any injury at all and look at the association between leg length inequality and osteoarthritis. That's one approach. It's not one I typically do because I like to maximize my sample. I don't like, if I have a lot of participants in a study, I don't want to take some of them out. So usually the approach that I end up doing is either adjusting or stratifying so that I still keep all participants in my study, but then I can account for what injury may be doing as a covariate to these analyses. So you can use statistical models where you include injury as a covariate. And then the other approach that you can use is also stratifying. So you can look at the association of leg length inequality and osteoarthritis among those who are injured, and then look at leg length inequality and osteoarthritis among those who are not injured, and then see how the results compare. So this is an example here. So this is real data from Johnston County, where we were looking at the association of leg length inequality and knee osteoarthritis. So this is our unadjusted estimate. And what you'll notice is after we adjust for injury, we do see that our odds ratio attenuates. It gets closer to the null, which is 1.0. So our results go from being statistically significant because our confidence intervals don't cross the null here to not being significant where the confidence interval crosses 1. So this is one where you can see that injury did play a role as a confounder. And so once we were able to control for it, we got a better idea of what the true association is. And then I'll give another example that's not from the OA area, but at least to give you an idea about what we do if a variable is on the causal pathway. So here, when we're looking at the association between poor diet and heart disease, we might consider obesity as a potential covariate. So if we want to look to see if it's a risk factor for disease, well, obesity we know can lead to heart disease. So we would say yes for the first response here. But when we're looking at the association between obesity and the main exposure, sorry, I keep losing my arrow. There it is. We see that it's not that obesity leads to poor diet, but poor diet more likely leads to obesity. So this is a situation where we do have obesity as an intermediate step on the causal pathway, going from poor diet to developing obesity that may contribute to heart disease. So we would not consider this a confounder. And what we would consider this instead is an intermediate factor. So this is one where we likely, if we were doing our models, we would not want to include it as for adjustment in models. You could still stratify association, or yeah, stratify your associations that you're looking at, but you would not want to control for it. And then for confidence intervals, so I want to bring this up because I think it's often a source of confusion. So there are a few different ways we can define the confidence interval as either being commonly at 90%, 95%, or 99%. Probably what I see the most in the literature is 95%. And it's not how confident we are that our results, the association that we found is correct. It's in fact this long definition here. So if the confidence interval is set to 95%, this means that if data collection and analysis were repeated many times, that the confidence interval would include the correct value of the estimate 95% of the time. This is not something that, I don't expect this to be easy to understand. It's something where it takes a lot of time to understand, and I think even there's still times that I get confused about exactly what it means. But the way that we end up using it is it's a measurement of precision, so that we know when we calculate our association, we get a sense of how precise our estimate is. And then one of my students a couple of years ago, he was trying, so he was working on his PhD in epidemiology, and he was trying to come up with another way to think about the 95% confidence interval. And I liked what he had to share. So he said that it refers to a hypothetical large collection of replicated analyses. So what you calculate is your study's contribution to the field. So I'll give some examples of what I mean about precision of the estimate and how we use that 95% confidence interval as well as p-value. So it's important when you're making your decisions on how to interpret your results that you get to look at the point estimate and how large it is or small it is, to look at that 95% confidence interval and how wide or narrow it is. And you can also look at the p-value. So often you can see that there are papers where they rely solely on the p-value for interpreting results. So I've seen some papers where they just put a star if it's statistically significant, so using that cut point of 0.05, and then they'll just put an NS, or not significant, if that doesn't meet the cut point. What's useful about including the point estimate and the 95% confidence interval is it can give us more of a sense of what's actually happening with our data and our results. So in this example here, the first one on the left, we have a point estimate that's high with the odds ratio of 3.0. But what you'll notice is that the confidence interval is what we call wide. So the lines are really long. And this would indicate that we don't have a very precise estimate. But this is one where if you were reading a paper where they only focused on the p-value, they would be very excited and call this statistically significant. But something like this, yeah, although I would be excited about the point estimate because it's not very precise, it should be interpreted with some caution, and probably part of the reason it looks like this is the sample size is small. For the next one over, what we see here is a point estimate of 1.2, which isn't high, but it does suggest a positive association. This one also has a p-value of less than 0.05, but what you'll notice is the confidence interval is pretty narrow. So this might be one where there was a much larger sample. So sample size can drive the precision of the estimate. So that's one where, even though it's not a huge point estimate, we would highlight that it's a precise estimate that we have. And then the next one over, this is one where some authors might not even report it because they would consider it not significant. But it's one that, there is a positive association. I would call this like a borderline statistically significant. It just overlaps the 1.0 null. So it's one where we have more precision with it. So it's always good to talk about, you know, all the factors involved here. That this might not be a result that you just want to throw out and ignore. There might be some usefulness to it. And then the last one is where you have an odds ratio of 2.5. But again, we lack precision. But it's still something that's, you know, worth noting when you're writing up your results section, that it is an interesting finding, rather than just overlooking it because it's not significant. Any questions about that? Yeah.
What counts as a large or like a wide confidence interval or narrow?
It's somewhat subjective. When I was going through my epi training, what we tended to do was calculation of the confidence interval ratio, where you took, you know, the top number divided by the bottom number, and you could get an idea of how wide it was. I don't know that there's, you know, generally when you're looking at your results, and I like to put mine in figures if I'm able to. Sometimes it can just be a visual like this that lets you know that you have more precision or less precision. And, you know, it's often just something you point out, but there's not like a real cut point or strong definition. Does that help? Or okay.
Could you explain the difference between a covariant and a confounder?
So a covariate is any variable that you think may be associated with either the exposure or the outcome. But the confounder is one where when you're looking at the association between that exposure and outcome, that it's actually altering the association that you see. So it's that, I can go back, it's that mixing of effects. So here, when we didn't adjust for injury, it looked like we had this really strong association between leg length inequality and osteoarthritis. But once we put it into the model, we saw that this association was reduced, and it was because the injury was through its association with osteoarthritis and its other association with leg length inequality, it was creating this false stronger association. So that's the confounder. A covariate is a more general term for just anything that we tend to look at our covariates, you know, things that we think are related to the outcome or exposure, and then we try to determine whether they might be confounders and we need to control for them, or whether they might be associated with just the exposure, and we might have to do some kind of stratified analysis or some other approach because we think that they may be modifying an association. So covariate's the broader term. Does that help?
Yeah.
Okay. Okay, so in summary, for talking about the cohort studies, it's important to clearly state your research question up front, because this can determine the study design that you use, whether you want to look at something cross-sectionally or longitudinally, and it can also determine the measure of effect that you want to look at. So as I mentioned, you might have to make a choice between looking at prevalence versus odds ratios based on how common your outcome is. And also if you're planning to do a longitudinal analysis, this would be one where you would want to look at incidence or an incidence rate. It's always important to define all your variables up front, so your outcome, your exposure, and your covariates, and then consider those those covariates that are potential confounders. And also consider more than the p-values. So look at the point estimate and its strength of association, as well as the precision from the 95% confidence interval. And I have one more thing to talk about, but related to case control studies, which likely you won't be doing, but I think it's an important topic because it comes up quite a bit. But were there any other questions before I move on from cohort studies? So the case control study is actually a special type of a cohort study. And what it is it's a very efficient way of doing a cohort study. So often with a cohort study, like Johnston County, it takes a lot of time, over 28 years up to this point. And it takes a lot of money, resources. And it's cohort studies, it's hard to get them funded. It's hard to follow individuals for a very long period of time. And especially if you're interested in looking at something where the disease doesn't occur very often, if it's more of a rare disease, an outcome that occurs less than 10% of the time. So that's where a case control study can be very helpful, and that you can do this efficient analysis without having to do the big cohort study. So I'll explain more of how that works. So essentially what you have to do is imagine the cohort study you would have done with infinite resources and infinite time. And what you would do is you would set up a case control study where all the cases that you bring in would have been the people that you would have brought in if you had done the cohort study. The trickier part is the controls. So the controls need to be a random sample of the source population for the cases. So this is if you did that big cohort study, what would your sample population have been? And then you have to find a random sample of those controls, those individuals that you thought would have been in your study. And in the best case scenario, you try to sample controls as cases come into your study. So it's important to know that with a case control study, it's not just a random group of cases and a random set of controls thrown together. And unfortunately, there are a number of publications out there where that's been the case, where they find cases that maybe come into a clinic, and then they identify volunteers from the community to be the controls. And maybe those cases and those controls, if you've done that big cohort study, they may not have been in that study. That some of these volunteer controls who were out in the community, if they had had the disease of interest, they might not have come into that clinic where you do have your cases. So you end up kind of comparing apples and oranges in those situations. So it's really important to think about that ideal cohort study first. So here it says that the cases and controls should have that logical relationship to one another, meaning that they would have come from that same source population. And one thing to be aware of, in clinical settings, it can feel like a natural laboratory, but sometimes that's not the case, and I'll give an example of a paper where that might have happened. And the other thing to be careful of when doing case control studies is matching. So there's this idea that when we're doing case control, that we should try to get our cases and our controls to be as similar as possible. So you may see papers where they match on age and BMI and sex and many different things. The problem with that is with that over matching, it can lead to bias. Because we really do want our controls to be a sample of the source population. And if we're concerned about some of those other covariates, they are things that we can control for in our statistical models. But we don't want to limit which controls we bring in. We do want them to be representative of who we thought we would have brought in if we had done that big cohort study. So as I said, matching introduces bias, and if matching is necessary, you try to account for that bias later in your analyses. So often when it comes to matching, we suggest using it only sparingly. So it may be okay to control for, or to match for age and BMI on your analyses, or when you're bringing in your controls, but you probably don't want to do more than just a couple, or you may just not want to worry about the matching at all. It all depends on your study. So this is an example of how not to do a case control study. So what we're looking at here, the investigators wanted to see familial predisposition towards tearing an ACL. And so they had brought in 171 surgical cases and then had 171 match controls. And I will go through some of their methods here. So their case group originally was 757 patients who'd all had an ACL tear and had undergone treatment at the Fowler Kennedy Sport Medicine Clinic. So the control group was originally 636 participants, and they had been recruited from several different places. So some of them were recruited from varsity teams at the University of Western Ontario, some of them from the Department of Kinesiology, some of them from Fowler Kennedy Sport Medicine Clinic, so the same place where the cases arose, and then also from secondary schools throughout Toronto. So what would have been ideal was to have controls be a random sample from the population that would have gone to Fowler Kennedy if they would have torn their ACL. So sometimes it's not always clear to us who those individuals could be, but that could be something when you're initially recruiting, where you include that on a questionnaire, just saying if you were to have this type of an injury, where would you go for your care? And that might help at least make sure that your control group that you're identifying, if you've done the big cohort study, they probably would have been a part of that. But here we start to have more of a convenience sample rather than one that's representative of who would have been in that cohort study. That makes sense. And then the other thing that they did with their matching criteria is they tried to make them as similar as possible, and they even say that. So they match for age within 5 years, they match for gender, they match for primary sport. So, you know, initially this doesn't seem like too many things to match for, although it's not necessarily clear why they wanted to match for sport. But what ends up happening with all this matching is they originally had many participants available, so 732, but once they started matching, they ended up not being able to achieve these ideal matches, and they threw away half of their participants for doing the analyses. So as I mentioned before, you want to keep as many participants as possible in your study. You know, it's good for many reasons. Trying to make sure that you have a more representative sample, but also you and the participants have gone through this effort of doing this research, and it's if you can use their data, use their data. So actually the bigger picture here was there was quite a bit of loss of participants for the final analyses that they did. So they originally had 757 cases, 636 controls, but they said in one brief sentence that they had excluded 661 because they had incomplete data. I don't know exactly what data were incomplete, but that's a pretty large number of participants that they removed. So they now had 53% of who they had originally. There are ways of handling missing data, and which is another conversation I'm happy to have. But again, we try to keep as many participants in a study as possible. And then we lost 390 due to a lack of match. So by the end, out of all the people that they had brought into the study, they ended up only using 25% of them for their analyses. So this is concerning because in the end, we're not sure that we have a study that's representative of what we would see for these types of associations when everything is just whittled down. So not to scare you away from case control studies, because they are very useful, but it's important as you're developing one to really think about that cohort study that you would have ideally done, and then make sure that you find all the outcome positive subjects first, which you would have done in that cohort study, and then you're trying to find that sample of those who are outcome negative that would have been representative of the controls or of the disease-free individuals that you would have seen in that cohort study. And whenever I think about designing a case control study, I don't sit and do it by myself. I talk with others, talk with other epidemiologists, with statisticians, trying to make sure that we design the best study that would represent what we would want to have as a representative analysis.